The first data structure we will investigate is dynamic arrays, which could probably be considered as the de facto default data structure in most modern programming languages. Dynamic arrays are extremely practical, as they can grow dynamically in size as new elements are added and preserve the order in which the elements arrive. In C# and Python, this data structure is implemented in a type named list. Java calls it an array list, and in C++ the structure can be found in std vector. Let's take a closer look at some common operation on dynamic arrays. First, the operation that adds a new element to the container. Dynamic arrays are, behind the scenes, implemented using an array with a static size. Here is an example of such a static array with room for 8 elements. Here in this example there are 2 free positions available. When a new element is added, it is appended to the leftmost empty position. Here the element 3 was added to the last empty position. So adding a new element is generally just a matter of writing to a certain address and keeping track of the position of the next available free position. None of these things depend on the size of the array, nor of the number of elements in the array. That is, the number of operations needed for adding a new element is the same number independently of the array size, or in other words, it is constant. So in general, the worst case complexity can be written as big O of 1, as we learned in the previous module. Occasionally, however, we reach the capacity of the inner static array, and when that happens, a new and larger static array is allocated. The elements from the previous array are copied to the new array, and the new element is appended to the end of the new array. Here I have chosen the number 2 as growth factor for simplicity reasons. The actual factor varies among concrete implementations. A factor of 1.5 is a popular choice, but it typically lies between 1, not inclusive of course, and 2. If we assume that there are n elements in the static array, the reallocation needs to copy all n elements to the new array, and append the last one of course. The latter takes a constant number of instructions, but the former either takes n individual copy instructions, or in practice one single memcopy instruction, but on a data amount that is in the order of n in size. Therefore, the worst case complexity of the element insertion is big O of n. Notice that formal performance analysis, which is what we do here, is independent on the hardware that stores the data structure. A dynamic array may not only be stored in main memory where an ultra-fast memcopy operation is available, but could just as well be stored on a slow magnetic hard drive, or even be implemented in the physical world using boxes and containers of incrementing sizes. Therefore, we cannot just assume that the copying of n elements only takes a constant amount of time. So, if it takes big O of n time to insert a single element, worst case, does insertion of n elements then take big O of n times n time, or big O of n squared? One should think so, but that's actually not the case. In this table I have written how many operations it takes to insert from 1 to 10 elements. First of all, it always takes at least n operations to insert n elements, because we need to spend at least one operation to handle each element. On top of that, we occasionally need to perform a reallocation. Let's try to walk through the insertion of the first 10 elements. If we assume we start with a static array of size 1, and in that we place the first element, there is no room for the second element. So we double the capacity, copy the single element from the previous array, and insert the second element. Now we have performed 2 insertions and 1 copying, as seen in the second row of the table. Sadly, when the third element arrives, the array is full again. So we double the capacity, copy the 2 elements from the previous array, and insert the third element. That was 3 element insertions in total, and 3 element copyings, namely the first, single one, and the 2 we just did. Now there is a little bit of room to receive the fourth element, but when the fifth element arrives, we are on it again. Once again, allocate a new array of double size, copy the 4 elements from the previous array, and append the fifth element. We have now performed first 1, then 2, and now 4 copy instructions, besides inserting the 5 elements, just as the table shows at row 5. The insertion now continues with elements 6, 7, and 8, but when element 9 arrives, we need an expansion again, requiring a total of 1 plus 2 plus 4 plus 8 copy instructions, besides the 9 element insertions, and so on and so forth. So, what does all this sum up to? Let's consider the insertion of element number 9. Take a look at this. This is 9 written in decimal to the left and as binary to the right. Just like a decimal number is the sum of its rightmost digit times 1, plus the second rightmost digit times 10, plus the third rightmost digit times 100, and so on, each binary number is also the sum of its rightmost digit times 1, plus the second rightmost digit times 2, plus the third rightmost digit times 4, and so on. So the sum of all the copy instructions performed when inserting element number 9 can be written like this, because these 4 digits represents the numbers 1, 2, 4, and 8. If we add the two numbers, we get the number representing the total number of instructions. And as you can see, this is only 1 digit larger than 9 written in binary. We could do the same with the next element that would require a reallocation, namely 17. Inserting 17 elements would cause 1 plus 2 plus 4 plus 8 plus 16 copy instructions. And together with the 17 insertions, this gives a number that is no more than 1 digit larger than 17 written binary. We can do this inspection with even larger numbers too, and we will always end up with a sum that is no more than 1 digit larger. For decimal numbers, you might know that adding an extra digit corresponds to increasing the number with an order of 10. Similarly, adding an extra digit to a binary number corresponds to scaling that number with an order of 2. But scaling with an order of 2 is scaling with a constant factor, and we know what that means. Constant factors can be ignored in this kind of analysis. Therefore, the amortized worst-case complexity of adding n elements to a dynamic array is not big O of n squared, but simply just big O of n. The analysis of removing an element is much simpler than for adding an element. Assume that we want to remove the value 57. This is simply done by copying all elements after 57 one position down. If there are n elements in the array, we will therefore need to copy at most n elements, and this worst case scenario happens at the leftmost element. In other words, the time complexity of removing an element is big O of n. It just strikes me that in our real-life investment analyzer example from before, the queue in which we put investment queries for trading gets a lot of elements added and especially removed continuously. That's a lot of copying around and reorganization for each and every item that leaves the queue. When we use a dynamic array, that is. Dynamic arrays doesn't really seem suited for that kind of job. Let's proceed to the operation of finding an element in a dynamic array, or a static array for that matter. There's no indexing structure, so in order to find a specific element, say 891, each and every position needs to be scanned until the element is found. Again, if there are n elements in the array, it takes big O of n instructions to perform the scan. Notice that this complexity does not only hold for operations that return the position of the element to be found, but also operations that return Boolean values. For the C# list data type, that includes the contains method too, that just returns true or false depending on whether the provided value is found or not. Consider our investment analyzer example once again. We used a list data type as a cache, but the search for a key is apparently really slow. And the more elements that are put in the cache, the slower the cache will find the key and return the associated value. That's a pretty unfortunate performance characteristic for a cache, which sole job is to be lightning fast.